Hello everyone, this is Harish Chandra Kumar and today I would like to explain you about the real numbers 10th class first chapter. Okay, student, in previous classes you have studied about number system such as natural numbers, whole numbers, integers, rational and irrational numbers. Now in today's topic of real numbers, I'll be explaining briefly about the number system and also the fundamental theorem of arithmetic and Euclids division lemma. Okay, let us begin our chapter of real numbers. Okay. Okay, a real number set is denoted by R. A real number set is denoted by capital R, and it is classified into rational and irrational numbers. Rational and irrational numbers. Rational numbers. Inside the rational numbers, we will be having an integer set and also contains whole numbers, then contains natural numbers. Okay, rational numbers contains integers. Further, we have whole numbers and natural numbers. Okay, now rational numbers can be expressed in p by q form. Okay, p by q form, where p and q both are integers, such as 2 by 3, 5 by 7, like that. So p comma q belongs to z. P and q are the numbers taken from integer set, and here q should not be equal to 0. Okay, so any number which is expressed in p by q form called rational numbers. Now when it comes to irrational number, it will be of the form root 2, root 3 and root 5. And these are irrational numbers, these are rational numbers. Now this is about the number system. Then we will go for Euclids division lemma. Okay, Euclids division lemma. Okay, Euclids division lemma. Now, before I start, what is lemma? Okay, do you know what is lemma? Lemma is a statement which is already proved. Okay, so using that proved statement, we are writing some more statements. Let us see an example. We can write 6 into 3. 6 is how much? 18. Is it true? Yes, it is true. 6 is 18. 18 is like a true statement we have taken. Now we divide 18 by 6. 6 ones are 6 threes are. So using this true statement, I will be writing one more statement. I can write some more statements such as 18 by 3 is equal to 6. Okay, so what is lemma? Lemma is a statement which is already proved. Using this, we are writing some more statements. That is called a lemma. Now, in Euclids division lemma, the process of division is involved. Okay, what is involved? Process of division is involved. For dividing, we must have at least two numbers, a and b. We'll consider two numbers, a and b. One being larger, so 15 and 7. When a is divided by b, that is 15 is divided by 7. 7 2s are 14. I will be getting remainder as well. Okay, so this is called remainder, and this is quotient and divisor, dividend. Now, so we compare remainder with divisor. I can see 1 is less than 7. 1 is less than 7. That means remainder, my remainder is less than divisor b. Okay. Now you also know that sometimes you may get remainder 0. Like when 7 is divided by 7. When 7 is divided by 7, 7 1 is 7, I will be getting remainder as 0. Okay, so remainder may be 0, equal to 0 or more than 0, but always less than b. Okay, so this is what division is about. Now when we divide a larger number with smaller number, during the process of division, I will be getting two new terms, q and r. Okay, what are q and r? They are whole numbers. Okay, whole numbers starting from 0, 0, 1, 2, 3. Okay, so q and r satisfying this one. 15 is equal to, dividend is equal to divisor into quotient plus remainder. Okay, so 15 is nothing but a is equal to bq plus r. Okay, dividend is equal to divisor into quotient plus remainder. 15, 7 2s are 14, 14 plus 1, 15. So here the condition of r is r may be 0 or more than 0 but less than the value of b. Okay, this is called Euclid's division lemma. Okay, so what it says, when two numbers are given, when we divide a larger number with smaller number, during the process of division I'll be getting two new numbers q and r, those are whole numbers, and satisfying dividend is equal to divisor into quotient plus remainder. Okay, so we'll take one more example related to it. A and b, we'll take 23 and 5. So 5 is the divisor, and 23 is the dividend. 5 fours are 20 and this is 3. Okay, this is quotient and this one is remainder. Now we compare remainder with divisor. Always we compare remainder with divisor. I can see 3 is less than 5. So length I can write r is less than b. Remainder is less than b, and sometimes remainder also 0. So I can write like this. So I want to represent this entire in the form of equation like this. So 23 dividend is equal to divisor into quotient, 5 fours are 20 plus 3 remainder. So a is equal to bq plus r. Okay. So condition of r is 0 is less than r less than b. Okay. This is Euclid's division lemma. What is Euclid's division lemma? When two positive integers are given, when we divide one number, the larger number with smaller number, during the process of division, I will be getting quotient and remainder satisfying a is equal to bq plus r. Okay, this is called Euclid's division lemma, and we have application of this one. Application of this one is Euclid's division algorithm. Okay, so let us see what is Euclid's division algorithm. Euclid's division algorithm. Okay. So algorithm is nothing but series of steps or series of well-defined steps. Okay, for understanding a problem. So series of well-defined steps. So we write step-by-step procedure for this one in order to understand in a better way. Okay. Now since division is there, so it is an application of Euclid's division lemma. This is an application of Euclid's division lemma. The same a is equal to bq plus r used. Okay. Using this one, we are mainly finding HCF of any two numbers given. Okay. So how do we write? We'll take an example like this. 88 and 56. So we consider this as A, 88 as A and 56 as B. Okay. Now we will divide a larger number is smaller number, A by B, that is 88 divided by 56. So 56 and 88. 56 ones are 56 and this is 2, this is 3. Take this 56 over here. 32 ones are 32, 4 and 2. Take this 32 here. 24 ones are 24. I'll be getting 8 and continue the process. 8 fours are 8 threes are 24. So the process of this division stops when remainder becomes 0. So when remainder becomes 0, the last divisor, this is called highest common factor. Okay. Now this one we represent for Euclid's division algorithm. See, what is dividend? 88. Dividend is equal to divisor into quotient plus remainder. Remainder is 32. Okay. 56 ones are 56 plus 32. Next, we'll take new dividend. This is new dividend. Okay. New dividend is equal to new divisor. Yeah. 32 into dash plus dash. Okay. 32 ones are 32 and remainder is 24. Yeah. One more time, 32, the new dividend 32 is equal to 24 into dash plus dash. So 24 ones are 24 and it is 8. Considering 24 once again, 24 is equal to 8 into dash plus dash. 8 threes are 24 and remainder is 0. So when the remainder becomes 0, okay, Okay, when remainder becomes 0, our process of division stops, and this is our highest common factor. Okay, say dividend is equal to divisor into quotient plus remainder, and once again dividend is equal to divisor into quotient plus remainder. Okay, so the process continues until we get remainder 0. Once remainder gets 0, our last divisor, this one is called HCF. We use the Euclids division algorithm for finding HCF of these two given numbers. Okay, so yeah, we'll see. Now we'll take another example. We'll take one more example like this. Take two numbers A and B, 23 and 24 and 18. So when I divide larger number, smaller number, 24 by 18, so 18 ones are 18, and I'll be getting 6, taking 18 here, 6 3s are 18, so the remainder is 0. So we represent this in the form of equation. So we get 24 is equal to 18 ones are 18 plus 6, and new dividend 18 is equal to new divisor into 3 plus 0. So when remainder becomes 0, this is our HCF. Okay, so using Euclid division lemma, we are finding HCF of two given numbers. Okay, HCF of 24 comma 18 is 6. Okay, so this is about Euclid division lemma. Okay, now we have fundamental theorem of arithmetic. So coming to fundamental theorem of arithmetic, you can take any composite number. Okay, any composite number, such as suppose if I take 10 or 20. So if I take 20 can be written as 2 into 10 and 2 into 5. So 20 can be written as, or factorized as product of primes. Okay, any composite number which can be expressed as product of primes is called a composite number, or factorized. We get the factors as a prime numbers. Okay, so this is called the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Okay, so the statement is like this: any composite number can be expressed as product of primes, or you can write every composite number can be expressed as product of prime. Okay, so this factorization is unique. Okay, what do you mean by unique? Same number of terms will repeat, 2 to 5 always, and you can also write 5 into 2 into 2, or you can write 2 into 5 into 2. So whatever the order may be, the repetition of numbers will be same. That is called unique. So this factorization is unique. This factorization is unique. Okay, that means same numbers will be repeated again and again, but the order changes. So that is what the fundamental theorem of arithmetic. Using fundamental theorem of arithmetic, we are finding LCM and HCF of given numbers. Okay, so we take some examples to find the HCF and LCM using fundamental theorem of arithmetic. Okay, we'll take somewhat 56 and 72. Okay, yeah. So how do we, since 56 is a composite number, I can express in product of primes like this. 56 in 2 table, 2 28s are, and 2 14s are, 2 7s are. So I can write 56 as 2 into 2 into 2 into 7. Or else I can also write this as in exponential form. In exponential form, I can write this as, can be expressed as 2 power 3, because 2's are 3 times and 7. Similarly, 72 can be written as 72. I can write 2 into 36, 2 into 18, 2 into 9, 3 into 3. So this is 2 into 2 into 2 into 3 into 3. So 2 power 3 and 3 power 2. Okay. Now how do we find HCF? See HCF, common factors using. Mark the common factor. This is common factor. This is common factor. This is common factor. We have 3 common factors. From these common factors we take 1, 2, and here 1, 2, and here also 1, 2. So 2 2s are 4, 4 2s are 8. 8 is my HCF. Now coming to LCM. Okay, LCM, you see this among the common factors, which is the highest? Is it 2 power 3 highest or 2 power 3 highest? So both are same. So we can take anything out of this one. We take 2 power 3. So when you are finding LCM, you focus on what exponential form. Okay, and yeah, non-common terms. This is common too, but here 7 is not common. You consider that also, and also 3 square. 3 square is like that. So 2 cube is 2 into 2 into 2. It will be 8 into 7 into 9. So it's if we multiply this one, we get 56 into 9. So I'll be getting 504 as LCM. Okay. So HCF is 8, LCM is 504. So using fundamental theorem of arithmetic, we are finding LCM and HCF of 2 given numbers. Okay. So when you are using, when you are finding LCM, you use exponential form so that it will easy. First you take the common terms, like common numbers you can consider. So highest among this one is 2 power 3 only. Then the remaining factors can be considered. Okay. Yeah, let us take one more example related to this. So 18 and 32. So 18 can be expressed as, or product of primes for 18 is 2 into 3 into 3. This is 2 power 1 into 3 power 2, and 32 is 2 into 2 into 2 into 2 into 2. So 2 power 5. Okay, HCF. HCF common is 2 we have. See, one common 2 is there. Okay, so HCF will be, yeah, HCF is 2, and LCM, coming to LCM, we have among common, this is the highest one. 2 power 1, 2 power 5, highest is 2 power 5. And the remaining term is 3 square. So this is 32 into 9. So 288 is my LCM. Okay. This is how we find the, using fundamental theorem of arithmetic, we are finding the HCF and LCM of 2 given numbers.